Welcome to this lecture where we're going to look at another alternative definition of the complexity class NP. First, we'll introduce the complexity class definer called nTime, and then we'll define NP in a different way. And then we're going to take a little detour and think carefully about nondeterminism, what it can and cannot do, and how it interacts with complexity. And then we're going to use this new definition of NP to prove that the Hamiltonian path problem, is also still in NP using the new definition and a new proof. The material, of course, is from CIPSR 7.3. We already know about the definition time. Time T of n contains all languages decidable in big O of T of n time by a deterministic Turing machine. And some sources refer to this as D time to emphasize the deterministic nature. N time is an analog to time, where n time of T of n contains all languages that are decidable by a T of n, big O T of n time, non-deterministic Turing machine. And we'll remember that the running time for a non-deterministic Turing machine is the length of the longest branch of its computation. So, given this new definition of n time, we can use it to define NP in a new way. Previously, we defined NP as languages that have polynomial-time deterministic verifiers. Now we have a new definition, and the new definition is NP is equivalent to a union over all k, where k is an integer, of n time n to the k. So this is all polynomial time. This is polynomial time, non-deterministic, decidable languages. And this definition is what gives the name NP, is where the name NP comes from. NP, it stands for non-deterministic polynomial time. And NP is the non-deterministic analog to the class P. Now, let's take our quick detour. Before we apply that definition, let's take a quick detour and think about non-determinism, what it can do, what it cannot do, and in particular, how what it can and cannot do interacts with complexity. In a non-deterministic algorithm, we make non-deterministic choices, and each non-deterministic choice causes the machine to sort of branch into multiple different configurations. And in this example right here, we might make one non-deterministic choice. Let's imagine that we're programming a non-deterministic algorithm, and we make a choice among 4 options, and the 4 options are 1, 2, 3, 4. The way to think about this is that we're in some configuration. We're coming down, there's a branch, and we're in some configuration in our non-deterministic algorithm. And once we make this choice, the machine splits itself into 4 different branches. In this branch, k equals 1, in this branch, k equals 2, k equals 3, and k equals 4. These branches have their own memory, they run independently of one another, and they have different values of k. And the important thing that I'm trying to make here, the important point I'm trying to make here is that what you see listed here is 1, 2, 3, 4. This is a fixed number of options, and that's what we're saying here. A fixed number of options is possible to make with one non-deterministic choice. And you can think of the number of options the number of options for any non-deterministic choice should be constant, should be fixed, and you can think of that as a compile time constant. But what it cannot be is it can't be a variable such as an input to the algorithm. It can't be something that's known only once we see the input. So let me give you an example of that. You cannot do something like this code right here. Read an integer from the input or from a file, okay? And then construct a list that has n elements in it. So n here could be 1,000 or 1,000,000, whatever. And then construct a list that's that long, and then make a single non-deterministic choice where we branch into n different configurations, where each configuration has one of those n options. We cannot do this non-deterministically in constant time, okay? Because a non-deterministic choice is always among a fixed number of options. If you recall our discussion on branching factor, that's the branching factor. Um, this isn't to say that it's impossible to make a non-deterministic selection among a variable number of things. We can do that, and I'll show you how to do that in just a second. The way we do that is to use multiple non-deterministic choices to select among a variable number of options. But every choice that we make when we select among a variable number of options, every non-deterministic choice must be among a fixed number of options. So here's a way that we could do that. Here is an algorithm that I just mocked up, which is non-deterministic and which would behave in the following manner. Suppose you had a set or a list called S, and you wanted to choose one element from that list non-deterministically. You can't do that in constant time, but what you can do is you can choose or not choose the first element, choose or not choose the second element, and so on. And that's what this algorithm does. It says, let's first compute the length of the list that we're choosing from, and then it loops up to n minus 1 times. Each time it loops, it makes a non-deterministic choice among just two options, and that's a fixed number of options, and it lets B be the Boolean value for which is false or true. And if the value that the branch gets is true, then it simply returns the ith element of the list. And if it's false, then it loops back again and makes another non-deterministic choice. And finally, if B has been false every time we make this choice, and we never returned early, then at the end, we return the last element of the list. Okay, so here's a visual depiction of what this looks like. If we call choose from and we pass in S, then the first iteration, one branch is going to return the first element, and the other branch is going to continue looping and make another non-deterministic choice. And then this second iteration, there's one branch that's going to return the second element and another branch that's going to continue looping, and so on. So eventually we're going to return all of the options, including the second and last one, and the last one in case no other option was chosen. Okay. What I want to emphasize here is that we're making fixed number of choices for each non-deterministic choice, and choosing among n options, in this case, the way I've written it, requires order n time. So you have to consider how many non-deterministic choices you make, the size of the thing that you're choosing from, when you're thinking about analyzing the complexity of a non-deterministic algorithm. A few more comments on what non-determinism can and cannot do. Remember that non-determinism is a useful model. That's why we use it in this class. It's also not real, but it's not magical either. We can't just imagine that it could do whatever we want. It has limitations. So it can do these things. It can branch on a fixed number of options in constant time, like we just saw. And all of the branches that get created, they run simultaneously and they run independently. Every branch also gets its own copy of the tape. It gets its own memory. And that seems completely unrealistic, and it is. And in addition, if any branch accepts, then the entire machine accepts. So it doesn't matter if all but one branch rejects, but one branch accepts, the entire machine accepts. So these are things that non-determinism can do. It can branch on a fixed number of items. It can run all those branches independently. It has each branch get its own memory, and it can accept if any branch accepts. However, non-determinism is limited in that it cannot do the following things. It cannot branch on a variable number of options in constant time, like we just saw. And in addition, branches can't communicate with one another. If I have, a branch here and a branch here, they cannot talk to one another. Of course, they might have some shared state from back here, but once this one has computed something, it can't share it with that branch over there unless they had some history that they have communicated in the past before they branched, okay? So no branch can inspect the computation of another branch, and there's no globally shared state except what's in the common history. Okay, so all of that said, those are the limitations of non-determinism and the possibilities. What I want to do now is describe a non-deterministic Turing machine for deciding the problem Ham path. And this is going to be a polytime nondeterministic decider. Let's call it n, and it takes as input a graph and two nodes, s and t. And the first thing that it does is it counts the number of vertices or nodes in the graph, and we'll call that k. Then it's going to construct a set of all the vertices except for s and t, because what we want to do is we want to come up with an ordering of the vertices between s and t, but not including those. And we're going to try to construct a path that goes from S through some sequence of all the other vertices and then ends at T. And P is going to be that path. So P initially is just the vertex S. So P is a list. It's a path that we're constructing. And it's initially just the starting vertex S. And then we're going to loop K minus 2 times to order these S vertices that we have here. Okay, these K minus 2 vertices that are in S. Then we're going to, at each iteration, we're going to do three things. We're going to choose a next vertex using the algorithm that we described earlier, this choose from algorithm. We're going to append that vertex to the path, and then we're going to remove that vertex from the set of considerations. Now, since this right here is a non-deterministic choice, or really a sequence of non-deterministic choices, the machine is going to branch into multiple branches at this line, okay? Or within the code of choose from. Okay, so what we're doing here is we're starting with S. We have a vertex S, and then we have K minus 2 vertices in the middle, and then we have T, and this is going to be our path P that we're constructing, and this path is going to be different depending on the order that we choose these vertices in the middle. Because finally, at the end, we append T to the path. That's where we get this T right here. After we've constructed, after each branch has, or this branch has constructed its path, P, it checks, is this a Hamiltonian path that starts at S and ends at T? Well, we've constructed it to start at S, and we've constructed it to end at T, and we've constructed it to be Hamiltonian in the sense that it visits every other vertex exactly once. So the only other question is this actually a path in the graph? And if it is, then this branch accepts, and otherwise this branch rejects. And the question is this a correct algorithm? Does it decide ham path? And in addition, what is its analysis? Well, let's think about what this algorithm does. We constructed N, which I claim is a polytime NDTM that decides ham path, because if the graph S and T are members of ham path, then there's going to be some branch of N that constructs the path from S to T and is going to accept. And since that one branch accepts, the entire machine accepts. But if G, S, and T are not a member of ham path, then there's no Hamiltonian path from S to T, then there's no way that any of the branches could possibly construct such a path because it doesn't exist. So otherwise, every branch of N rejects, so N is going to reject. Okay, so this is my claim that N is a decider for ham path. And in addition, the running time of N is polynomial in G, S, and T. So let's see why that is. Let's go back and see why that is. Counting the number of nodes in G can be done in polynomial time. Constructing a set of all those vertices can be done in polynomial time. And then this loops k times, or n times for n vertices, or k times for k vertices on that order. And each of these operations, that's going to be an order k operation, because remember that this algorithm back here takes order n time. Well, if we have for n things, here we have order k things, so this is going to be order k. Draw that a little better. Order k. So we have order k loop, and we have order k decision process in here. So this is going to be on the order of k squared at least, but the point is that all of this is Hamiltonian. Let's not leave out the fact that we have to check that within this branch that it's a Hamiltonian path, and that can of course be done in polynomial time, because the verifier could do it in polynomial time, and here essentially all we're doing is verifying that the path is Hamiltonian. the path that we've already constructed. So I'm not going to give a specific order to this polynomial, but I think you can trust me, or believe that this is a polynomial time algorithm because each portion of this algorithm is polynomial time. So the end of our proof then is because n decides Ham path and it does so in polynomial time, Ham path is a member of NP. This is applying the new definition of NP that we have. So now we have two definitions of NP. We have a previous definition from a previous lecture that A is a member of NP. A is a language that belongs to NP if A is polynomial time verifiable by a deterministic verifier. And then from this lecture, we saw that A is in NP if A is decidable in polynomial time by a non-deterministic Turing machine. So we have polynomial time deterministic verifiability, and we have polynomial time non-deterministic decidability. And these two are different definitions, and it's not entirely clear that they are the same, that they define the same class of languages. So in the following lecture, we'll unify these two definitions and show that they are equivalent.